let me begin by saying just a few words about his background. He was born in 1954 in a family of medical doctors, but he did not become a doctor. And in fact, he studied in elementary school and high school in Belgium, and then enrolled in the Free University, and he studied mathematics. And how come mathematics from a family of doctors? Well, at an early age, he discovered at home some books in elementary calculus. And he got curious. And this is a way in which, in fact, many mathematicians have started their first contact with the subject. A famous case, for example, is the one of Sonia Kowaleska. Well, he did very well, and so he got rather quickly a position from the Belgian Science Foundation, which allowed him to be completely free of duties except doing research. And so he visited often the French institution, in particular the École Polytechnique, and the mathematical centers in Israel, in Jerusalem, and Tel Aviv. And there he learned new subjects. In particular, that's where he learned his first area of really most significant research in convex sets. In 1985, he was appointed to the IHES faculty, the Institut des Hautes Études Scientifiques in Bourgain, in France, and also a half-time position at the University of Illinois. And so his research expanded to harmonic analysis, ergodic theory, partial differential equations, and continued at a very active pace. And in the 90s, he began studying evolution of Hamiltonian systems, Hamiltonian equations. And in 94, he joined the Institute for Advanced Study, the same year in which he was awarded the Fields Medal for his study in mathematics. When he arrived at the Institute, a little later, quite a bit of new activity in the area of combinatorics and computer science started, and that turned out to be quite influential in his most recent work. In particular, making a quick example, the famous Kakeya set problem, which the original question is related to the following. Suppose you have a needle in the plane, and you want to rotate the needle 180 degrees, and you ask, what is the minimum area of surface that you have to span in order to do the rotation? And it turned out it's not immediately obvious, but the area can be arbitrarily small. And this problem gave origin to very, very delicate questions about the ultimate structure of Euclidean space. And in fact, mathematicians work in any number of dimensions, of course. And Bourgain has contributed quite a bit to the questions. But now, in fact, his techniques and his ideas have been combined with not just with the classical harmonic analysis, but also with the discrete mathematics associated to combinatorics and computer science. Case in point is the recent studies about the so-called sum product theorem, which really discovers incredibly subtle properties about the difference of behavior of the elementary operation of sum and the elementary operation of multiplication. All this comes once again, in the previous lecture we heard a bit how the theory of groups may help to understand the evolution of biological forms. And in this case, Bourgain again will talk about lecture, the title, Expansion, Linear Groups and Applications. And this time his groups are in a sense of the similar nature of the one mentioned by Milner in his previous lecture, except for the fact that will be in a context, will be related to finite fields and discrete mathematics. It's one more example of the fact that the theory of groups of transformations is pervading today all of mathematics, and is certainly excellent. There are excellent topics for our lectures. Please.
So thanks, Enrico, for the introduction. Very happy to talk here for this occasion, for this 80th anniversary. So in this talk, what I like to do is describe some mathematical developments in the theory of expansion in the Cayley graphs of certain groups. So perhaps it will be a little bit more, mathematically speaking, a little bit more technical than the previous talk, but not too technical, I hope. And then also, depending on how much time there is, and there's probably not going to be too much time, I will show you some of the applications, say, new applications and applications to problems that were around of these new results. So let me recall you that expander graphs are sparse graphs with high connectivity, and they have many applications. Originally, many of these applications were really somehow connected to theoretical computer science. There were applications to error-correcting codes, de-randomization, efficient communication networks, and so on. But then later, there have been also more mathematical applications, and especially now with the new results, the theory as it is shaped now, there are quite a bit of perspectives, and in particular there are applications to topology, to group theory, geometry, number theory. Of course, I don't have much time, and I will probably concentrate on giving you one rather nice application to number theory, although there are others, and also some applications to quantum computation and to geometry. But again, it will depend on how much time there is left at the end. So maybe a good place to start, although probably most of you know these concepts, is what is meant by an expander graph. So what we are considering are, so what is written here are sparse graphs with high connectivity. So let's be a little bit more precise about that. So sparse, what we're going to do is look at undirected k-regular graphs where k is a fixed number. So k is 3 or 4 or something. And so k, you should think of a fixed number. And the graph is on a very large, say, finite vertex set V with n vertices. So that means that every vertex has k neighbors in this graph. And since the number of edges is proportional to the number of vertices by a factor k, we are calling it sparse. But we are really going to talk about k-regular graphs for some fixed k. Now, the expansion property of a graph can be expressed in several ways. One way is to talk about the vertex expansion property and the Cheeger constant. So what does it mean that we have an expansion property? It just means that if we take arbitrary sets S, say, S is a subset of the vertex set, which is at most half of the size of the vertex set, then we're looking at the ratio between the size of the boundary of S and the size of S. And we want this ratio to stay away from, to be bounded from below by a constant that stays away from 0. So basically this expansion property means that for arbitrary subsets S, the size of the boundary is kind of proportional to the size of the set S. Now the boundary of the set S is defined as the collection of all the edges which are going from S to the complement of S. So for instance, in this picture here, you have the set S, which are the 3 points above, and then you can look at the boundary, which are going to be the 6 edges that are connecting points of S to points outside of S. So expansion means that subsets have a large boundary, and the quantity which is on the left there, h of g, is usually called the Cheeger constant. It minimizes this ratio over all subsets, or says at most half of the vertex set. Alternatively, there is a spectral interpretation. I'm just recalling some background here, which is going to reappear later in this talk. And one can consider the adjacency matrix of G. So G was a graph on n vertices. It was undirected, so we have a symmetric graph. The adjacency matrix being defined as the matrix which is 1 if ij is an edge and 0 otherwise, we obtain an n by n symmetric matrix which has n eigenvalues. Recall that G was k-regular, so clearly the largest eigenvalue with eigenfunction, say the constant function, is going to be k, and then we can order the next eigenvalues, they are real of course, in decreasing order. So there is a relation between the following quantities. There is the Cheeger constant introduced before, and there is the gap. This is what we call a spectral gap between the largest eigenvalue and the next one. So another way to express expansion is just by requiring that the difference between the top eigenvalue and the next one remains bounded away from 0. So if we have a control from below on this quantity, we get a control, because of this inequality, we get a control from below on h of g, and conversely. Now, of course, if you have a graph which is connected, you're going to have such a gap. But what do we really mean by expansion and expander families? So what we should do is look at sequences of graphs. So we fix a k, and then we look at a sequence of k-regular graphs on vertex sets which are getting larger and larger. And we say that this family forms an expander family, provided over this family of graphs you have an expansion coefficient, a Cheeger constant here, which remains uniformly bounded from below by a constant, which is strictly positive and may depend, and of course will depend, on the chosen family. So it just means that you have a collection of graphs, say k-regular graphs, on larger and larger vertex sets, for which this expansion coefficient is uniformly controlled from below. So after having explained to you the concepts, it's also natural to continue with something like the earlier history of expander graphs. So the question is, do such families really exist? And truth of the matter is that the existence of such families is not intuitive at all. As a test, say, if you would try it out on somebody who does not know the subject, he may very well quickly tell you, well, tomorrow I'll come up with a simple argument that such things cannot exist. So it's not at all obvious that these things do exist. But anyway, Pinsky in 1973 showed that generically, if you take a k regular graph, say with k at least equal to 3, fixed on a large number of vertices, you're going to have a uniform expansion. In other words, we're getting a probabilistic construction, a probabilistic existence proof of the existence of expander families. We just look at an increasing value n for the vertices and take random, k is fixed here, regular graphs on these n vertices, and we get the expansion coefficient, which is with high probability going to be controlled uniformly from below over n. Now, it was pointed out to me, and I think that makes a nice subject for a little digression here, that this whole idea of looking at probabilistic, at the probabilistic version of the problem is already implicit in some work that was pursued by Kolmogorov and Bourgain in a really applied context, which has to do with the realization of networks in 3D space. So this was related to studies in cybernetics, and the problem that these guys wanted to understand is the following. Assume that we have a mathematical graph, say, which is k regular, and k, again, k should always be thought of as a fixed number, say 3, on a large number of vertices. So we have this mathematical graph there, and then we want to realize this graph in physical space, in 3D physical space, with wires that have a certain thickness. Well, you can say you can take thickness delta, but let's take thickness 1. You just have to rescale the whole thing. So, for instance, you have some network. You have to stuff in a space shuttle. I don't know. You have a limited amount of space, and you want to understand from the nature of this graph how much space you really need. So this is probably unreadable, but it does not matter. What I want to point out is that the final version of the paper is due to Bourgain. Apparently, Kolmogorov, what he obtained were results that were slightly weaker. So the two theorems I'm going to cite next are the final answers to this problem. And they are the ones that are stated in the paper I just pointed out. The first theorem is that you can always find a realization. So the G twiddle is the physical realization of the graph with the wires. Well, you can always find such a realization of the graph G in a ball of volume, in a ball of radius about square root of n. So the volume is n at the power 3/2. Now, more important in this discussion is that n at the power 3/2 is the best you can do, at least generically, because what they prove next, using probabilistic considerations and arguments that are probably not so far away from what Pinsker does, is that if you fix k and you take a typical nk graph, so k regular graph on n vertices, any realization G twiddle of this graph will require n at the power 3/2 volume. So I have to acknowledge that I did not really read the paper in very great detail, but let me give you my explanation for what is going on in the second theorem from, say, a more modern perspective and also from the perspective I want to discuss. So what we know is that these graphs are going to be expander graphs. And the reason why theorem 2 is true, it's quite simple, is because expander graphs, they require much space. They have good properties, but they also require much space. And how do we see that? Well, assume that you have a G twiddle, which is a realization of this graph with some wiring. We don't specify how. Then we can do the following. We take an arbitrary two-dimensional plane H, and we are translating H to a plane H prime, so that we have about half of the vertices on the left and half of the vertices on the right. So with a little bit of goodwill, for a typical plane H, you're going to be able to do that. But now we know that you have an expander graph. So in other words, you have at least 1/2 hn edges that have to connect something from the left with something to the right. So you got these 1/2 hn wires that have to cross all that plane H prime. So the area of the intersection of H prime with the realization G twiddle has to be at least 1/2 hn. And at that stage, being a harmonic analyst, was not very difficult for me to make a connection with a well-known result in harmonic analysis of Euclidean space, which is due to, I think it is due to Oberlin and Eli Stein, which is telling you that if you have a situation, if you have a solid in 3 space, and every 2-dimensional plane can be translated to intersect this solid in an area which is at least something, then the volume has to be at least the 3/2 power of this quantity up to an absolute constant. And you get n3/2 like that. So that is a way to explain that second theorem of Barzin and Kolmogorov. Now, still early history, the next question is assume that we are not interested in existence. We really want to find such things. So we don't have access to pure randomness. Well, if you don't have access to pure randomness, you try algebra, because algebra is also quite complex science, at least for me. And there may be some choice of some hope to match, complexity you find in probabilistic structures by the complexity from algebraic structures. So the first algebraic construction was given by Margulis, but more relevant for our discussion are Cayley graphs on groups and Selberg's theorem. Here I left a slide. This was from an earlier talk. This was really meant for a non-mathematical, absolutely non-mathematical audience. So without insulting your knowledge, let me just recall you that if you have a group G and a set S of, say, set S of generators of G, you can associate a Cayley graph. So we are going to take this S symmetric so that the graph is undirected, it's a symmetric graph. So the Cayley graph X is the graph which will have as vertices the elements of the group G, and then the edges, well, you're going to join 2 elements X and Y from the group if their symmetric difference lies in S. Okay? And so what is quite relevant to us is the theorem of Selberg, which was rather restricted, and that is the first thing we are going to elaborate. Now we are at the end of the earlier history. Is that if we take for the group SL2P, so these are 2x2 matrices over the prime field Z mod PZ with determinant 1 mod P. So this is a finite group with how many elements? P minus 1, P plus 1 number of elements. Well, you can turn these groups, well, you can find suitable Cayley graphs on these groups that will give you an expander families, in other words, with a uniform control on the expansion. But Selberg's theorem requires you to make judicious choices of these generators. Because what he showed was the following thing. So the way we're going to choose these generators is quite specific. What we're going to do is start from, say, a finite collection of matrices in SL2Z. So now we're taking the big SL2Z. So we take a finite collection of matrices in SL2Z, so take it symmetric. And then what we will do is consider the reduction mod P. So we look at things only mod P. We get this pi P map from SL2Z to SL2 over the field P. And, well, we get a Cayley graph by taking pi P of S. Now, the important assumption, which is necessary to formulate Selberg's theorem, is that the group generated by S in SL2Z, it's not just anything, but we assume that it's either all of SL2Z or at least a finite index subgroup of SL2Z. So that's a very strong hypothesis. So then what follows from his work is that if we take P sufficiently large, and we are looking at this family of Cayley graphs, So we have, they are going to be k, regular with k, the size of S. The vertex sets are going to be increasing in size with p going up, and we're getting a uniform expansion property. The expansion property being dependent on S. Alternatively, you can describe this by fractional linear maps as follows. Instead of looking at the group as vertex set, this is a bit in the spirit of the previous talk, you can take the projective line over Fp. So basically we get as vertex set, we get Z mod Pz. So if we would consider a particular instance where Selberg's theorem applies, where S is the set given by the matrices A and B, and then we so that will satisfy the assumptions, and we are looking at what happens on the projective level. Then we see that these graphs are obtained using very simple rules. So there is absolutely no question how explicit they are, because we are just joining from the first matrix x to x plus 1, and its inverse is x minus 1, and then we join x to 1 over x also. So we have three edges, three outgoing edges. X goes to x plus 1, x minus 1, and 1 over x. So these are simple rules. These graphs have a uniform expansion property, and as you can see, the structures obtained are quite complex. But there is a catch, is that the choice of these generators is quite special, because we really need to have the generators coming from higher up there in SL2Z, generating basically the full group. So this problem was illustrated quite well in a folklore question, which is due to Alex Lubotsky and is known as the 1, 2, 3 problem. So what is described, what is given here are three sets of potential generators. So you have S1, S2, and S3, and they are almost the same, except that you change 1 to 2 to 3. So S1, S2, S3 are subsets of SL2Z. S1, S2, they generate a finite index subgroup, so the Selberg theorem applies, and reduction mod P gives you a family of expanding graphs. On the other hand, what turns out is that S3 is not generating a finite index subgroup. In other words, if you look at the group generated by S3 in SL2Z, it's not finite index. On the other hand, for P sufficiently large, a reduction mod P of the group generated by S3 is still giving you all of SL2P. So Lubotsky's problem was, how do we show that the Cayley graphs associated to this S3 are still going to have a good expansion property? Because it kind of looks immoral if the first two are okay, that the last one, which looks almost the same, wouldn't be okay. Now, this problem remained unresolved actually for quite a while, until now we are getting to the more modern history, some recent advances which provide in particular a robust theory of expander Cayley graphs for groups SL2P. And these are techniques which are based on what Enrico referred to as more combinatorial, arithmetical combinatorial techniques. So what was shown, what we showed, is that actually if you take any set S of generators for SL2P, so SA has a fixed size, in order to have a good expansion property, what is enough, it's not necessary, but what is enough to require is that in this graph we don't have loops which are small compared with log P. So if there are no closed loops, if any closed loop in this graph is of size at least, say, delta times log P, then there is a uniform control on the expansion coefficient of the corresponding Cayley graph by a function that only depends on this delta. So in particular, most generator choices of SL2P provide good expansion. In fact, there are even stronger conjectures around, but I don't want to go in that. And more relevant for the context of Selberg theorem is that if we now start from a symmetric subset of SL2Z, I called it S before, now let's call it lambda. So lambda is a finite symmetric set in SL2Z. I'll take it always symmetric for, I mean, you don't really have to take it symmetric, it's actually irrelevant here. So we have a finite set lambda in SL2Z. Now, instead of assuming that the group generated by lambda is finite indexed, I just assume that it contains the group generated by lambda, I call it gamma, that gamma contains the free group on two generators, or equivalently, that it is a non-elementary group. That is a much, much weaker assumption because this group, lambda, can be an extremely thin group. So then the statement is that if we take P large enough, reduction mod P is going to map the group gamma on all of SL2P. If you want to have expansion, the first condition is that you should have a connected graph. So you need to have, if you restrict the reduction mod P to the generated group, the image should be onto, so we're getting all of SL2P, and moreover, we have if we vary P, we have an expander family with an expansion coefficient that, well, let's say that is certainly controlled in terms of the original set lambda. So this is a much stronger statement. And as we will see, that has several applications. But before I get to such applications, I should slightly broaden up the setting and talk about a conjecture that was formulated by Lubotsky and Weiss, which is exactly the same spirit, but only a little bit general. So instead of taking SL2, I'm going to take SLD. So I will start with a finite a finite subset S of SLD over the integers. And well, if D is larger, it's not enough to require that the group generated by S contains a free group. We have to assume more. What we need to assume is that the group is Zariski dense in SLD. So the smallest algebraic group containing S is going to be all of SLD. If you're not familiar with this notion, it doesn't matter because I'll explain you in a while where it comes in. So instead of looking just at primes, we will take all possible integers. And so the statement is that there is some Q0 depending on S, so that when you look at all these graphs on SLD, Z mod QZ, so here you take SLD over the ring Z mod QZ, with so the Cayley graph associated to the reduction mod Q of the given set S, well, we have a uniform expansion family for this whole, uniform expansion coefficient for this whole family, provided we take the Q, the modulus Q, relative prime with Q0. So what is this, the role of this Zariski density? Well, this is another interesting piece of mathematics. This is classical. It is a strong approximation property. And proven by Matthews, Wasserstein, Weisweiler, and later there's a proof by Pink. It tells us that if we have a subgroup G of SLD, Z, say, which is Zariski dense in SLD, then we have this phenomenon, this is where the Q0 comes in, say, that there is a Q0, so that if we take the restriction of the map pi Q, the reduction mod Q, to the subgroup G, we get something which is onto SLD Z mod QZ, provided Q is relative prime with Q0. So that is, for the same reason, we had this restriction Q co-prime with Q0, because of course you cannot have an expander graph, a family of expander graphs, if these graphs are not connected. You need to have connected graphs. And connected means that the map should be onto. Of course, it's not because you have, well, I mean, if you have this connectedness, you're going to have some gap, but there is nobody that tells you that this gap is going to be uniform. So that is a non-trivial thing. It turns out that this Lubotsky-Weiss conjecture is true. That is one of the things that was completed recently, say within the last 2 years, and there are many, well, there are a number of contributors to this project, and I list them there in alphabetical order. And I should also say that results of that type were obtained beyond the integers. They were also obtained in the context of number fields, which is also important for certain applications. Now, there are applications I will not at all talk about here. There are applications to topology, in particular a program initiated by Mark Lackenby on the Heggard gradients of curves of hyperbolic tree manifolds. You can read that in his ICM presentation, the recent ICM Congress, if you want. What I'm going to talk about is a nice application to number theory, which actually depends on two other developments, which depend very much on the theory I just described you, but I don't have time to go into that. The first is Selberg's eigenvalue theorem for hyperbolic quotients, in particular hyperbolic surfaces, where we get a generalization going from congruent subgroups from SL2Z to congruent subgroups of non-elementary subgroups. That allows you to start doing lattice point counting with the various methods at hand in hyperbolic space using techniques developed by Lax, Phillips, Lally, and others. And the application I want to show you to number theory, which is an application to prime sieving in the orbits of linear groups, actually uses it's based on having the two developments related to Selberg's eigenvalue theorem, the generalization of it, and to methods in the application to methods in hyperbolic lattice point counting. But this can be explained in a fairly non-technical way. So it is an application to Apollonian circle packings. So let me recall you Apollonius theorem, which is easy to prove by inversion and tells you that if you have three mutually tangent circles, then there are exactly two circles tangent to all three. An easy way to prove that is by inversion. So once you have this tangent, you have these four initial tangent circles, you can start filling in the loones by further tangent circles, each of them tangent to three circles, and given exactly by Apollonius theorem, giving what is called Apollonian circle packings. Now, when I started searching the internet, I found that there is actually quite a bit of study of these Apollonian circle packings and also Apollonian networks, which were proposed as models for various things. Say, to go back to biology, they were proposed as efficient neural networks for the brain. Also issues about electricity distributions, say in the western United States between, that's what it seems to say, between different power plants and that kind of stuff. Now these properties, the spectral properties of Apollonian networks are quite interesting, but that is not exactly what I'm going to describe here. What I want to pursue is a line of research that was initiated by Graham, Lagarius, Mallows, Wilkes, and Yan, and that has to do with the Diophantine properties of curvatures in integral Apollonian circle packings. So let me start by mentioning a result that apparently goes back to Fred Soddy. He was got a Nobel Prize in chemistry. Not really clear why he was interested in integral Apollonian circle packings, but anyway, what he observed is that if we start from our four circles here, having an integral curvature, then all the later curvatures are still going to be integral. And the reason to explain that is that there is in fact a quadratic form, which is a Descartes form, which is a quadratic form in four variables of type 3-1, and the vanishing of f is equivalent with x1, x2, x3, x4 being curvatures of four mutually tangent circles. The curvatures obtained in an Apollonian packing are obtained by starting from the root quadruple, which are the four curvatures of the initial four tangent circles. Here you have 6 for the outer, minus 6 for the outer circle, 11, 14, and 23. And what happens is that all the later curvatures you get in this packing are obtained as the orbit of a group. You look at the orbit script O, A, which is the orbit of the root quadruple A under the so-called Apollonian packing group. which is generated by S1, S2, S3, S4. These are integral matrices. They also have an integral inverse, so it's clear that everything remains integral. And this Apollonian packing group is a discrete, finitely generated discrete subgroup of the orthogonal group. And, well, you can start studying that with the new developments in spectral theory we have and the standard machinery. But before I tell you something more about that, the first question you can ask yourself is how many integers do we really get in such an Apollonian circle packing? Because we are generating integers there, I mean, you get many circles, but maybe you don't get so many integers. So let me reassure you that every Apollonian integral circle packing, if you look at the set of the curvatures, you get many integers, you get the set of positive density. So once mathematicians have a nice set of integers, what is the next thing they are interested in? It's the problem of primes and twin primes. So assume given a primitive Apollonian circle packing, we can introduce prime circles, which means that the curvature is a prime, and also twin prime circles, which are tangent circles, each of which have a curvature which is prime. And we can try to count them, look how many we have with possible repetition, considering all curvature at most equal to t. Now, it turns out that if we just look at the number of curvatures with possible repetition in a given Apollonian circle packing, all curvatures at most equal to t, then the order of magnitude, here we are counting with repetition, is t to the power alpha, where alpha is some specific number, which is actually the residual dimension of the packing P. So what we should conjecture in analogy with what happens in number theory is that for prime circles we have to divide by a logarithm of t, and for twin prime circles we should divide by a square of the logarithm of t. So what Kantorovich and O showed is that these are actually the right upper bounds, and that depends on the whole machinery I just described. Of course, you like to have lower bounds. No, lower bounds is not so easy. It's not known. I mean, in the integers that you have infinitely many. The solution to the twin prime problem is open for the integers. So you should not hope too much. But what can be shown is that these numbers are actually the right order if we weaken a little bit. So instead of talking about prime circles, we can talk about pseudo-prime circles, requiring that the curvatures are written, say, in at most, if you factor them in primes, so you factor the curvature as an integer in primes, you require that the number of factors, say, is at most equal to 151 or something. I'm just giving you some number. It's some specific number that can be calculated. So I don't have much time. What I want to say you a little bit about is that there is a completely parallel theory, which is actually quite powerful, that has been developed for continuous groups. So in particular, you can consider the unitary groups. You can look at SU2, or more general, the group SUD. And what we showed is a quite powerful theorem, which is really much more conceptual than the special instances of this theorem that were known before. So we're going to start again from a set S, a finite set, lambda in SUD, which consists of algebraic elements. This algebraic element assumption, that corresponds to what we did earlier of taking things that come from SLDZ, right? It's not clear that this is necessary, but let's assume that the elements are algebraic, and in most of the applications they're algebraic. Now, the assumption of Zariski density, well, that should be formulated by requiring that the group generated by lambda, which is a subgroup, a discrete subgroup of SUD, is topologically dense. Well, under these assumptions, we can introduce a Heck operator, and this Heck operator has a spectral gap. Now, in Lehmann's words, what does it mean? Well, we are introducing an operator T acting on functions on the group, the L2 space of functions on the group, just by averaging the left translation, say, by elements G in that set lambda. So this operator, because we take lambda symmetric, is a self-adjoint operator. The top eigenvalue with eigenfunction 1 is the size of lambda, and what is proven is that for everything which is orthogonal to the function 1, the 2 norm of T of f is much smaller because we have this gap there by an epsilon. And this is a very, very strong statement. Let me ask you, how much time do I have? 0? 1 minute? No minute? Few minutes. So I cannot talk about all applications. Historically, the oldest application is perhaps the Banach-Kruziewicz problem. But more to the point for this discussion are applications to stochastic tilings considered by Conway and Radin, initiated by Conway and Radin. What I want to do is, because it's quite close to what I just said here, is say how these things are relevant in quantum computation. So I'm skipping a few things here. So in quantum computation, I don't know anything about quantum computation, and I'm not sure how much I want to know about it, but at least in the connection with this discussion, there is a nice application that people really cared about. Operations on say, qubit states are performed by unitary matrices. And for the sake of fault-tolerant quantum computation, what one likes to do, what one does, is expressing general gates, so general elements of SU2 or SUD, approximatively as words, products, short products of elements written in an instruction set A, which I will call base gates. Because these gates, these special gates, can be more fault tolerant. So the problem is, if we start from a set of base gates, that would be my set lambda, they are usually algebraic, which generates a group which is topologically dense, how well can we approximate an arbitrary an arbitrary element of SUD by a short word in A? So the Solovey-Kitaev algorithm, which is completely general, gives you a polylogarithmic length in epsilon in the approximation for the length of the words required, and moreover, as a bonus, the sequence, this approximation, this word can be produced with an algorithm with a very short running time. Now, on the other hand, what the obvious volumetric arguments are going to tell you is that if you want epsilon approximation, you cannot do better than words which are of length log 1 over epsilon. Problem, is it true that if we have such a computational universal instruction set, it's also going to be efficiently universal in the sense that we can reach an approximation using words of length log 1 over epsilon? So the answer is yes. Before there were examples, but now we have a general theory, and the answer is always yes, at least for algebraic instruction sets. What remains a problem is how to produce it. So Solovey-Kitaev produces fast approximating words which are polylog in 1 over epsilon, polylog in epsilon. We know that there are words which are, say, log of size of the order of log 1 over epsilon, but contrary to Solovey-Kitaev, we don't have an efficient way to produce them. So I already went over my time. Thank you very much.
We have time for a few questions.
I didn't catch the results about the lower bound on the number of primes you get in this.
For the
you had upper bounds. Do you have lower bounds too?
We definitely expect so. Proving upper bounds is considerably easier. There are tools, in fact, also developed by Selberg here at Brunn-Selberg, sieving techniques. These tools, they provide lower bounds, but only for pseudoprimes. So basically, the point is that the upper bounds for primes and pseudoprimes are about the same. But the lower bounds, to get that same quantity as a lower bound for primes, this is out of reach right now. So we have to weaken the notion to pseudo-prime. And pseudo here has a specific meaning. So there is some absolute number, I don't know whether it's 151 or maybe a slightly larger number, that will tell you that you have not only the upper bound but the lower bound if you weaken the notion of a prime circle to that of a pseudo-prime circle, where pseudo refers to that particular number. That is the state of things now, and I don't think it's going to change very quickly. That's my feeling.
Okay, thank you.
Was done on purpose. I didn't leave much time for questions, so it cannot be haunted too much.
Can you tell what are the next problems, open problems? The big open questions.
Well, the big open question, I'll tell you, and this is a question which is, I mean, should have an affirmative answer. Recall that I mentioned you in the statement that we are assuming these elements to be algebraic. The natural conjecture is that this theorem should be true without assuming that lambda consists of algebraic elements. So this runs into very subtle, what you may call Diophantine issues, and say offhand the first reaction would be that such things should be wrong. But there are certain recent developments, which uses quite a bit of number theory, in particular the theory of heights, combined with other methods that indicate that there may be a way still to do such things, and I definitely believe that it should be true. So this is definitely an interesting line of research, and so it's really, I think it is really at the interface of several developments. On one hand, we have methods, but then to feed these methods, we need a certain input, and I hope eventually this input will come from one or another Diophantine property, which will be true without assuming that the given elements are algebraic, and that such things happen, and there are indications that there may be such a theory. So this is one of the developments I like to pursue. That's what I'm going to put in my next NSF report anyway. So. Yeah.
You may want to try to get explicit constructions with expansions that is as good as in random constructions, not by the eigenvalues, because the explicit constructions, some of them are as good as possible in terms of eigenvalues, but not in terms of expansion.
Absolutely, but it's a shame I didn't have time to present you the rest application to the stochastic tilings, because what it shows there is that the spectral gap, at least before there were experiments by various people, and the spectral gap was really at the best at the third decimal. So it was extremely tiny, and when they made these conjectures about spectral gaps, these conjectures were very daring, because checking your operator on spherical harmonics of degree, 258 or something, already gave you a gap which was like in the third decimal. From there, making a statement about a conjecture about the spectral gap looks to me very daring. So eventually this conjecture was true. But what it shows is that the poor results you get, qualitatively speaking, from these arithmetic combinatorics, this is the reality, because the gap is not good. It's not as good as in a random graph. So still you are supporting the evidence for an experiment, and the experiment is showing that this gap is not as good as what you mentioned there. So I don't know whether you can upgrade these things and get better expansion, but the primary goal was to explain expansion in certain concrete models, where perhaps this expansion is by far not as good as in a random graph.
Okay, and one more question. So in the when you have the Solovay-Kitaev algorithm, somehow I got the impression that your running time there was smaller than the length of the sequence?
There are several versions.
So
there are several versions. What they took was the version which is in the paper of Dawson-Nielsen, which is a report of 2005.
Okay.
I would be very grateful if somebody has later references. I also should warn you that the book of
how
Nielsen contains mistakes. I mean, the book of Kitaev contains certain inaccuracies.
Okay,
in the
but can it
reference.
be, so the running time, you have to write down the sequence, right? Can you show
Well,
us
I
that?
have no clue how this is. I mean, if I didn't do the calculation, basically the thing is like an exercise you play with these bicommutators, and then you have to check carefully. I mean, the instructions is certainly polylog, so it's very conceivable that you have a running time which is of the same length. Now, I don't know exactly. I didn't make this calculation, so you're concerned with. Sorry, to come back to that here. This is. So you are concerned with the exponents 397.
That the second number is smaller than the first one.
Which is strange, right? Which is strange. So I may have miscopied this thing.
Okay. Okay.
So you are definite about it? I mean, it looks strange. I would have preferred to have that number down there and this one up there.
May I make a comment on that one? I don't know anything about
Who's
quantum.
talking?
This is Charles Simoni, and from the
Oh, I'm
computer
sorry.
science point of view, there are string searching algorithms in computer science where the search time is shorter than the string length. So it is not necessary to look at least for a sequence, to find it, but to find out whether a sequence exists in a string. You don't need to look at every character, and the search time can indeed be shorter than the string length.
So this is not a priori
It's not,
contradictory.
at least in the non-quantum case, and if you are looking for a particular pattern, it's not a priori wrong.
Well, thanks a lot for rescuing me because I was really in a state of panic. I think we have to stop.